In video 28 on the Foundations of the Computational Economics course, we're looking at the classical and very important problem, which is the model of bus engine replacement by John Rust. So this is really a classical paper, the optimal replacement of GMC bus engines, an empirical model of Harold Zerker, which was published in Econometrica in 1987. This paper is foundational on many levels, but the main point is that it develops the framework which is still extensively used in many fields today. So the paper has a fairly simple dynamic model. It's a binary choice, discrete binary choice model with a regenerative optimal stopping problem. And what that means is that it's the optimal stopping, like the deal or no deal game, but then when the stopping decision is taken, the problem simply regenerates and starts all over again. The paper has a smart solution method. John offers a poly algorithm to solve this kind of a problem. And as we've seen in several videos before, the combination of several algorithms is many times the good way to approach a complicated computational problem. Now, probably the most important contribution is the coherent econometric specification that John comes or offers, and given that he develops a new estimator, the maximum likelihood nested fixed point estimator, which is also a classical estimator for dynamic discrete choice models nowadays. And the application in the paper is very real. Actually, it is based on the data which was collected by a real person who John knew himself, named Harold Zerker, from the, if I remember correctly, Madison Bus Company. Anyway, the method that this paper develops now, more than 30 years later, is still an extremely powerful and useful method for dynamic models. We even had this comment in Econometrica in 2016 arguing this point. So let's remind ourselves, what are the components of a dynamic model? Remember, we have to define or understand what the state variables are, so we have to define the state space. These are the variables that describe all relevant information about the model decision process, so they have to include everything which is important for the decision that we want to model. Then decision variables themselves, they describe the choices that the economic agent has. Instantaneous payoffs or flow payoffs, this is the utility or profits or something like that is received by the economic agent in each time period. And then the motion rules, this are the transition probabilities, the equations or distributions that describe how the state space changes, the state variable change when we go from one period to another period, conditional on, of course, where we were, so in sort of in a Markov chain type of way, and conditional on the action, because the actions may change the evolvement of the state space. Now, it's important to emphasize here that these motion rules, they represent not necessarily the actual physical rules of motion in real life. On the other, instead they represent the beliefs of the decision maker of how things behave, right? So it's the beliefs which may or may not be correct that this decision maker has about how his or her actions would change the distributions, the motion of the state variables and the distribution of possible state variables in the next period. And then the solution of a dynamic model is given by the value function, or value functions in each time period in the finite horizon case, and the policy function. The policy function, just to remind you, is a mapping from the state space into the action space. In other words, it prescribes the optimal action for each point of the state space. That's what it's for. So in the Zurcher problem, the choice set is to either keep the engine on the bus or to replace the engine on the bus. And each bus comes into this repair shop that the superintendent runs once a month. And the decision is to either just do the ordinary maintenance on the bus or do the complete overhaul or replacement of the engine. And of course, replacement is costly, as well as maintenance. Replacement is an additional fixed cost, but there is a cost in the delays of the services that these buses provide. Now, what is that Zurcher sees about the state of the bus? What is the state of the problem? What are the important pieces of information that go into the decision of keeping or replacing? Well, obviously, he sees a lot of details about the bus. But probably one of the most important of such details is the mileage that the bus has made since the last engine overhaul. And this is the one variable that John Rust focuses on when modeling the replacement decisions. So the assumption is that, how far the bus has driven since the last overhaul of the engine is the most important piece of information in deciding whether or not to replace the engine. So what about the preferences or the reward in each time period? Well, it's all about minimizing costs. So therefore, you see a lot of minus signs here. And let's say that the function c is the cost of maintenance, which is parameterized with some parameters, theta1. And of course, if we replace, if dt equals 1, replace the engine, then the cost corresponds to the cost of completely new bus. Well, new, quote unquote. It's a bus with new engine. Whereas if the engine is not replaced, then the C is calculated at the level of X, which is the mileage at period T, right? So then and presumably it's more costly to maintain the buses with higher mileage because they just need more attention. Replacement cost is given by RC and is only paid if the engine is replaced. Now, what about the motion rules? So we've agreed that the state variable, which basically is the whole state space, is the mileage of the bus. But this variable is continuous. So we will actually look at the continuous state models later in the course. But here we just follow what John did, and it's that he discretized the range of traveled miles into bins and treated these bins as a completely discrete state space. So instead of thinking about how many miles the bus would drive in a particular time period, in a particular month, we are thinking about the transition probabilities of going from a bin with a lower number of miles into a bin with higher number of miles. And each bin is then characterized by a particular number of miles, with the first one is 0, new bus, or new engine. And remember, these miles are counted from the last overhaul of the engine. So this is a really nice way to cast the problem with continuous state space into a problem with discrete state space by just introducing the bins. So all we have to do to think about now are the transition probabilities of a bin with a particular number of miles into a different bin with a different particular number of miles. And instead of thinking of axes as miles, now we can think of axes just as indices of these bins. And so the indices, can run like all indices in natural numbers. Now, Rust makes a further assumption. He assumes that, he looks at the mileage data for all these buses. And it looks like, there's only a range of miles that the bus may run in 1 month. And so he assumes that in the next period, the bus can move up at most so many steps in terms of the bins. So in terms of difference between the miles on the odometer in period t+1 and in period t, there can only be so many bins that the bus could skip. And this is given by capital J. And then we can just parameterize the probabilities of moving up 1, 2, 3, and up to j steps, or staying in the same bin, which corresponds to j equals 0, with some parameters which are called here theta2, and they're just vectors of parameters which give transition probabilities of moving so many steps up. And by doing this, you can see that the probability of going to another bin, if we're not replacing the engine here, is independent of the xk, so the bin in which the bus is in the current period. So essentially, the probabilities of the increasing mileage from any existing mileage are the same. Okay, all of this wordy descriptions can be summarized really nicely in the transition probability matrix, which is the same matrix that we looked at when we talked about the Markov chains. The current period miles are here, and the probability of going from 0, the first row corresponds to 0 miles, new engine, into 0, 1, or 2, and these are bins now, right, are given by this vector. And you can see that this vector is repeated in each of the row of the matrix, except in the end you have to do some maintenance to ensure that this matrix is stochastic and the rows sum up to 1. Of course, this is the transition probability conditional on not replacing the engine. What happens if the engine is replaced? Well, then whatever was the mileage that the bus came in, because the engine is replaced, it's like starting from the new bus. And so it's this one vector which is repeated in every row. And of course, this is the same vector as here in the first vector corresponding to the new bus. So replacing the engine is the same as making the bus look as if it's new and hasn't driven any miles. This is going to be important. Now let's look at the dynamic optimization problem. We assume that Harrod-Zerker minimizes the costs, right? And that's equivalent to maximizing these payoffs that we had specified 2 slides ago. And this is going to be a discounted problem. It's going to have an expectation because the miles transition with some randomness. And what else to say? It's also an infinite horizon problem now. So there is no finite and terminal time period where the bus company closes down. Right. Let's in maximizing this expression here, the expected discounted reward, we need to find the policy function which essentially maps the state space into the decision space, as I mentioned. And so if we use this policy function to determine the decisions, then this expression here is maximized. As before, let's introduce the value function, which is the maximum attainable value at each period t. And what is that then? Well, that's the the same expression as before, but started with period t. That's all the difference. And now we also introduced the capital pi notation to denote the space of all of the functions, all of the policy functions that give this relationship. And we need to find such a policy function that maximizes this expression here. Right, now once we've defined the value function, we can write the Bellman equation right away. The Bellman equation is as before, this recursive expression where the value function is on the left-hand side, but also enters on the right-hand side, applied to the x prime, which is the next period state. and that's given by the motion rule of the problem. And the maximization operator is over the decisions. Decisions are to keep or to replace. And then here we have the instantaneous payoff plus the discounted expected value from the next period. So this corresponds one-to-one to the general Bellman equation that we saw in the previous video. Let's talk about Bellman equation and Bellman operator. Well, see, this expression can be thought of the equation in functional space for the function for the value function v of x. It could also be thought of as an operator, and this is the way we treated it last time when we were working with the inventory problem or coding up the inventory problem. There was an argument as an input to the function, which would give the function in the period t plus 1, and there was an output from the Bellman function that we coded up, which would give the result of calculating the right-hand side here. Well, we can we can think more systematically of this and talk about the Bellman operator. What's this operator? It's an operator in functional space. It's an operator t that takes in some function v of x, puts it into here, and calculates this whole expression to get the new function v of x, and this function is going to be an operator of the initial input. That is basically one iteration of the Bellman equation. And then the solution of the Bellman equation is just given by the fixed point of the operator, right? The whole Bellman equation can be written as the application of the operator to a particular point x in the state space. And this has to hold for all points in the state space. But the solution of the problem, the solution of the Bellman equation, is just a fixed point of the Bellman operator. And here's the important difference that I want to highlight between the finite horizon and the infinite horizon model. Well, as it follows from the from the term itself, right? There is a finite period capital T in the finite version of the problem. And this is the period where the Bellman equation does not have the second discounted expectation term. And in the finite period, there's no future, so there's no future to talk about. It's also typical that this finite solution is very simple and can be just given analytically. But if not, then we have to maximize the just the current period payoff in the capital period, in the capital T period. Now, value and policy functions are time-specific, as we saw in the inventory problem, depending on which time period you're in, and so how much time is left until the terminal period. There may be different solutions, or slightly different solutions. And then the backwards induction is the method to solve this finite horizon problems. We just start computing the value functions in the very last time period, and then we go backwards over time to calculate the value and policy functions for all time periods, and we naturally stop when we go all the way back to the first time period. So all of the examples in the previous video were finite horizons. Now, in the infinite horizon model, there is no such thing as the capital T, so we can say capital T equals plus infinity. And the value and the policy functions now cannot depend on time, right? They are time invariant, so the Bellman equation truly becomes a functional equation. And the way to think about the solution of this infinite horizon problems is that we need to calculate the fixed point of the Bellman operator. That's what we're doing. We're solving the functional Bellman equation in the space of the value functions, or equivalently, we're looking for a fixed point in the functional Bellman operator. Now, there is a theory that we will talk about specifically in one of the future videos, but here let me just say that according to the contraction mapping theorem, or Banach fixed point theorem, if you have a complete metric space, any complete metric space. So that's basically a space of objects where you can measure distance between subjects, and you have a contraction mapping defined in that space. Then this mapping admits a unique fixed point, okay, such that the fixed point equation holds. And moreover, this fixed point can be found by a repeated application of the operator t. So in other words, if you apply t many times, n times here, as n goes to infinity, then the result of this application approaches the fixed point itself. Well, as you will see, Bellman operator is a contraction mapping in the functional space, and therefore we can formulate the very simple algorithm that just follows from the fixed point theorem. And this algorithm is, we need to initialize the value function at some value, doesn't matter which value, and then solve Bellman equation to compute the Bellman operator's returned new function t of v, and then repeat this step many times until convergence, until the situation where we are close enough to the fixed point, unique fixed point of the Bellman operator, and then we're done. Then we've computed the value function that solves the Bellman equation, and along with it, we also computed the policy function. Remember, the policy function is just the point where the maximum in the Bellman equation is maximized. Interestingly, we can start with any initial guess, and that's because according to the theorem, it can be found by the fixed point can be found by repeated application of the operator. Anyway, you can start with any initial value of the value function VFI algorithm. These three steps are called value function iteration algorithm, value function iterations algorithm, and it is globally convergent. So you can start anywhere in the functional space of value functions, and by repeated applications of the Bellman operator, you will converge to the fixed point and the solution of the Bellman equation. Now think of the resemblance to the backwards induction. In backwards induction, we had to start with a particular value function which corresponded to the capital T, and then perform repeated applications of the Bellman operator until we reached the first time period, and then the whole solution to the problem was calculated. In value function iterations, we are pretty much doing the same thing, except that we can start at any point of the functional space, so at any initial values for the value function, and then we stop not when we reach the initial time period, the first time period. We stop when we reach convergence, so that v and t of v don't differ too much. But otherwise, in terms of the implementation of the code, the finite horizon problem and the infinite horizon problem are pretty much pretty similar. All right, so this is what we had to say about solving the Rust model. But as I mentioned in the very beginning, the paper is a lot more than just the application of value function iteration. Oh, it's a lot more than just solving the model. In particular, let's talk about how the model is made suitable for empirical work. Remember that Zurcher observes many different attributes of the buses that come into the workshop, and we only paid attention to one, the mileage, and we want to explain how replacement decisions are taken conditional on this observed mileage on the bus. of course, if we look at the actual data, there will be a lot of inconsistencies of the form that buses with the same mileage would be, taken into the overhaul of the engine or not. How do we explain that? Well, a good explanation is just to admit that we don't see all of the characteristics of the buses that come into the workshop. And so it's like we're having some error terms which contain the information that the econometricians do not observe, whereas Harold Zucker does observe that information. These error terms will allow the predictions from the model to be non-degenerate, and so we can form some likelihood of the data that we observe. There are three independent assumptions that John Rust came up with. The error terms are independent across observations of buses in this case, and this is due to random sampling. The error terms come in pairs. There is an error term for each of the discrete decisions, and this is a technical. A convenient technical assumption. Well, it's important to also assume that these error terms are independent across choices. If the two buses have the same mileage, whether or not they had been to an accident that had to lead that would require the replacement of the engine, that accident event would be independent across buses. And now, conditional on X, there's no serial correlation in the error terms. So every month, every time period, these error terms are independent from their previous period realizations. All of these assumptions are not necessarily true for the buses example, but these are kind of typical assumptions that we have to make when building an econometric model, and they are very convenient in the model that we are working with. So let's see what sort of convenience these assumptions offer. First of all, even if we cannot observe these epsilons, the error terms, they are in a state space, isn't it right? This is the information that the decision maker, Harold Zucker, observes when making the decisions on the replacement of engines. And so, according to the general form of the Bellman equation, these epsilons have to be inside of the arguments of the value function here, and potentially inside of the rewards. And also here we have to condition on the current values of all of the state space, of all of the state variables when calculating the expectation. And we also have to specify the motion rule for this additional state variable that would define the epsilon prime, the next period value. Okay, so first of all, let's write this expectation as a double integral. Now that we have two different state variables, we can integrate over each of them using some joint distribution of these variables. And remember that epsilon itself has two components, but the utility will depend only on the component with the particular choice. That's how this is set up. So for each particular d, it will be the component of the vector epsilon that plays a role in the current rewards. Rust made three key assumptions. Additive separability in preferences. So the error term can be additively separable, or is additively separable from the rest of the utility. This is a slight misuse of notation here, but the idea is clear. The utility function depends on the observed state and observed decisions, and the error term is just added to it. And this immediately takes us into the area or realm of random utility functions, or random utility modeling, which underlines all of the logit family of econometric models. So as soon as we see this, well, especially together with the third assumption that the epsilons have the extreme value type 1 distribution, that should hint us on that there will be logit formulas in this model. Now, the conditional independence assumption says that the joint distribution of the observed and unobserved states can be factored in this way. So the observed states have their own transition probabilities, and then conditional on the realization of the x prime, we have epsilons being realized as well. In the bus replacement model, this is actually also simplified to just the unconditional distribution of the error terms. Okay, so with the Rust assumptions, what we can do then with the Bellman equation, we can rewrite it in a particular way. First of all, you can see that now, because of this separability, we can calculate the integral over omega over this unobserved state separately, right? Take this out. And use the value function and this probability distribution to calculate the inner integral. Now we can also write the utility function. This is the same utility function that we specified in the beginning of this video, which has to do with the minimization of costs. And the additional term is just, you know, separate and as an additive term here. What's going to be really important is the max stability property of the extreme value type 1 distribution. And the max stability essentially says that the maximum of the random variable distributed in this way also is distributed in the same, with the same law, although the parameters have to be updated. Let's see exactly what's going on. So first of all, because the error term is additively separable, let's call everything except for this error over here a v of xd as a separate function, which is the deterministic part of the decision-specific value function. It is decision-specific because this value function is not only dependent on x, the states, but also on the choices. And this is the deterministic part of the decision-specific value function because we are not taking in the error term here. So let's just make the new notation, this small v of xd. Then we can rewrite the Bellman equation, this new Bellman equation, which has the error terms, as this simple expression. It's just that maximization of the deterministic part plus the error. Okay? Now this term, and I've written it as with arguments with primes, but it doesn't really matter, right? We can calculate it any arguments. Now this particular function enters here. And when we calculate the expectation of this with respect to epsilons, we rely on the max stability property because look at this. We're calculating the maximum of something that is just the extreme value distributed random variable shifted a little bit along the vertical axis. So this expression here has extreme value type 1 distribution. The maximum has the extreme value type 1 distribution according to the maximum stability, and that means that we can calculate this whole inner integral according to the known analytical distribution laws, and in the end of the day, analytically. This expected expectation of the value function. So this inner integral can be written in this form here, right? So everything in these brackets can be written in this analytical expression, which is referred to as a log sum. The log sum function introduced by Dan McFadden in his work on social surplus. This is simply the log of the sum of exps of the deterministic parts of the choice-specific value function calculated for two different choices, 0 and 1. You can see that this is the d that comes as a second argument of this deterministic part of the choice-specific value function. So this function here, the log sum function, it is the analytical expression for the inner integral, or the expectation over the extreme value distributed shocks. That enters into the integral over the transitions of x, and together this what now becomes the expectation of the value function. Right, so all we have done so far is just we have rewritten the Bellman equation, taking in the rest assumptions in this model. Okay, now let's look more precisely at this expectation of the value function. And let's make it a new notation, EV. This is what I will be calling the expected value function. This is a value function of states and decisions. This is the function of states and decisions. And it is written, it is given by this integral that we just saw on the previous slide. Okay, what's nice about it is that now we can plug this expression into the definition of the deterministic part of the choice-specific value function, and have this expression as well. Remember, the small v of x of d is defined here, and now we called everything with the integrals EV. So the small v of xd is simply the current utility plus beta EV, and that's what it says here. Well, look at these two lines. We have EV on the outside and we have small v over here, and we can just plug in this expression into here and into here, and we get an equation again. It is a transformed Bellman equation, and it is written in the new space, in the space of extreme, in the space of a expected value function. So this is just the transformation of the Bellman equation in the expected value function space. Now, of course, this integral here can be written as a sum, because the x's are discrete, and so this can be thought as the transition probability from x to x prime, and that comes from the transition probability matrices that we had written earlier. And so in the end, what we have is we have the expected value being equal to the sum, and plugging in the expressions for the small EVs. Oh, I have to make this smaller, I believe, to fit everything. We have an equation where EV is on the right hand side and also EVs are on the left hand side, except that notation is not perfect here. It doesn't need this. This is just the expected value function. We've made a special notation, so it should be just like that. Right. And you can see that there's expected value function on the left-hand side and the same thing on the right-hand side. This is a Bellman equation, just written in the expected value function space. And it looks a little bit different because we have included all of the assumptions that Rust had made. So we have the analytical expression for the expectation over the epsilons, and epsilons disappeared from here. And what else? And we sort of inverted or rewritten the Bellman equation in such a way that the maximum is no more here as well. It's replaced by the expectation of the maximum, which has the analytical form. Okay, we can now form a new operator, T star, in the expected value function space. And this will be given by this expression here. And we can solve it in the same way as we did before, using the VFI algorithm. Moreover, you can it happens to be that this new operator is also a contraction mapping, so the algorithm completely works. except that now it's in the expected value function space. Now, why it would be good to do it this way? Why is running it in expected value function space better? Well, see, here the function is of the arguments x and d, where x is the mileage and d is just 0 or 1. Whereas if we had to work with unobserved state variables, then we would have x as the mileage and epsilon. And more than likely that epsilon has a larger number of values than d. And so we are reducing the dimensionality of the fixed point problem by going into the expected value function space. It is also numerically more advantageous to work with the smoother functions EV rather than the value functions itself. And as we will see in the next video, there are nice numerical optimization possibilities still unexplored, and we will do that when we implement this model. Now, just to hint of where it's going next, because of the assumptions of the unobserved states that the econometrician doesn't see, but the decision maker does, we will eventually form the choice probabilities for different actions, for different Ds, depending on the state space. And they will take the form of the logit probabilities, as I hinted to a little bit earlier. These logit choice probabilities, they are a consequence of the assumption of the extreme value distribution of the unobserved states. But then, of course, why is it that important? Well, if we observe in the data that for a particular mileage, a particular decision was taken, then rather than to say, okay, this is incompatible with the model, which would be the conclusion if we didn't have this flexibility of errors, of error terms. Rather than that, we can say, okay, the probability of that event is this. It's given by this expression here. And that means that we can calculate the likelihood of the observed data for any combination of d and x. And this will eventually give rise to the likelihood estimator that we will look at the very end of this course. Okay, for further learning resources, you can read about John Rust a little bit more in Wiki. There's the link to the paper, and you can see that the paper, this paper, the Rust 87, has been cited many times and essentially gave rise to a whole new literature of structural estimation of dynamic models. Okay, till next time.